what if the strangest object in our solar system right now isn't a planet, asteroid, or moon, but a visitor from another star carrying secrets we're only beginning to decode? 3. I-Atlas, the interstellar comet that's rewriting assumptions about how objects from beyond behave when they encounter our stellar neighborhood. And right now, it's doing something that has astronomers worldwide captivated and puzzled. It's brightening, not near our star where heating drives activity. Far from solar influence, where physics says it should be fading into darkness, getting brighter as it moves away, defying thermodynamics, violating predictions built on studying thousands of local comets. So what's really happening deep inside this frozen traveler? What processes operate in materials formed around other stars that we've never encountered in our solar system? And what might this mysterious behavior reveal about the diversity of chemistry existing throughout our galaxy? When telescope systems first detected 3I Atlas in July 2025, it appeared unremarkable initially, just another faint, moving object among thousands cataloged annually. Standard detection protocols began. Calculate orbit, determine trajectory, assess composition. Then orbital analysis revealed something extraordinary. The velocity was wrong. 58 kilometers per second. Far too fast for solar orbit. The trajectory showed hyperbolic geometry. Eccentricity greater than 1. Mathematical proof that this object originated from interstellar space and would return there after its brief passage through our system. Not bound by solar gravity, not captured into any orbit, just passing through on a one-way journey from darkness back to darkness. The third confirmed interstellar visitor in human history, following Oumuamua's bizarre transit in 2017 and Borisov's conventional appearance in 2019. But as observations accumulated, 3I Atlas established its own unique identity, different from both predecessors. Refusing to fit comfortable categories, spectroscopy revealed chemistry that shouldn't exist in typical comets. Carbon dioxide dominating overwhelmingly. 8 parts carbon dioxide to 1 part water, complete inversion of normal cometary ratios where water dominates by similar margins. This inverted chemistry reflects formation around a fundamentally different type of star with different temperature profiles and elemental abundances. But the chemistry goes deeper than simple ratios. Spectroscopic analysis detected complex carbon chain molecules, organic compounds indicating chemical processing under conditions unlike our protoplanetary disk. Hydrogen cyanide signatures suggesting chemistry relevant to prebiotic molecular formation. Crystalline water ice structures that form only under specific thermal histories. These aren't just random molecules. They're chemical fingerprints. Each compound tells stories about temperature, pressure, radiation environment, and available elements during formation billions of years ago around a star we may never identify. 3I Atlas carries preserved samples of ancient stellar chemistry, locked, frozen for cosmic ages. The same building blocks found in protoplanetary disks around distant stars, the ingredients from which planets form, the materials that eventually, under right conditions, might lead to chemistry complex enough to support life, all present in measurable abundances in this wandering relic from the early galaxy. Comment below. What would you most want to analyze if you could study 3I Atlas samples directly? As 3I Atlas moved through its closest approach and began the long journey back toward interstellar space, astronomers expected predictable behavior. Activity should decline as solar heating weakens. Brightness should fade as sublimation rates decrease. The comet should become progressively dimmer and harder to observe as distance increases. Standard cometary physics built on centuries of observation says this must happen. Sublimation is driven by solar radiation heating. Farther from our star means less heating. Less heating means less sublimation. Less sublimation means fainter brightness. Simple cause and effect that works reliably for every solar system comet ever studied. 3I Atlas violated this ironclad pattern. Instead of fading predictably, it brightened, not slightly, substantially. Measurements from multiple independent observatories confirmed the same impossible result. The comet was getting brighter as it moved away from peak solar heating, violating thermodynamics at the most fundamental level. Objects don't spontaneously increase temperature when they move into colder environments. Heat flows from hot regions to cold regions, never the reverse. This is physics so basic and thoroughly tested that finding violations would require rewriting textbooks. Yet multiple telescopes measuring 3I Atlas brightness independently reached identical conclusions. The observations are real, the brightening is happening, and standard thermal models cannot explain it. So what could drive this impossible behavior? Several hypotheses exist, each with supporting evidence and problematic aspects. First possibility, delayed outgassing from subsurface reservoirs. Perhaps solar heating during perihelion penetrated deep into the nucleus, warming buried ice layers. That heat propagates inward slowly through low thermal conductivity materials. Days or weeks after peak heating, deeply buried volatiles finally reach sublimation temperature and begin venting. This delayed response could produce brightness increases after the comet has already moved away from closest approach. This mechanism operates in some solar system comets. Subsurface heating creating delayed outbursts. But the magnitude and duration of 3I Atlas brightening exceeds what delayed heating alone typically produces. Something more than simple thermal lag seems required. Second possibility, exotic chemistry releasing energy. Perhaps compounds formed under different stellar conditions undergo reactions when exposed to solar radiation for the first time in billions of years. Exothermic reactions, releasing heat that drives additional sublimation beyond what solar radiation alone provides. Chemical energy supplementing thermal energy. This requires specific chemistry, molecules that remain stable during interstellar travel at near absolute zero temperatures, but become reactive when warmed. Compounds that release energy when transitioning between states or reacting with other species present in the nucleus. Possible but unproven without direct sampling and laboratory analysis. Third possibility, structural changes exposing fresh material. Perhaps perihelion heating fractured the nucleus. Cracks propagating through the interior, fresh surfaces containing volatile-rich material becoming exposed to solar radiation. New active regions opening that weren't accessible before. Maximum heating stressed the structure. This could explain sudden brightness increases, but requires explaining why fracturing would occur after perihelion rather than during maximum thermal stress. Perhaps delayed structural failure from thermal fatigue. Perhaps pressure buildup from subsurface gas production, finding weak points and fracturing material days later. Each hypothesis has merit. Each explains some observations while struggling with others. The truth might involve multiple processes operating simultaneously, delayed heating plus exotic chemistry plus structural changes, all contributing to the anomalous brightening pattern. But determining which mechanisms actually operate requires observations we cannot currently make. We need direct sampling, laboratory analysis, measurements that remote spectroscopy cannot provide. Until that becomes possible, 3I Atlas brightening remains genuinely mysterious. Subscribe now, because what we're discovering next makes this mystery even deeper. Recent observations revealed another layer to 3I Atlas, anomalous behavior. The brightening isn't smooth and continuous. It shows periodic variations. Pulses, brightness increasing, peaking, declining, then increasing again in semi-regular cycles. Astronomers describe this as periodic brightness pulsations, not random fluctuations from measurement noise, not gradual monotonic changes, distinct pulses, suggesting internal processes operating on regular timescales. Each brightness pulse could indicate pressure changes deep within the nucleus. Imagine subsurface chambers where volatile ices exist under pressure from overlying material. As solar heating penetrates and these buried ices begin sublimating, pressure builds. Eventually, pressure exceeds the strength of overlying material. Fractures open, gas vents explosively. Brightness spikes as suddenly released material expands into space. Then the vent clogs or pressure equalizes. Activity declines, brightness fades, but heating continues. Pressure builds again in other chambers or the same region after material shifts. The cycle repeats, each pulse representing another pressure release event, as the nucleus slowly responds to thermal energy absorbed during perihelion passage. This isn't a literal bomb in any dangerous sense. No chemical explosives, no nuclear reactions, just natural phase transitions of ices under varying temperature and pressure conditions. But metaphorically, it resembles a clock mechanism. Periodic releases governed by physical processes that operate on predictable timescales. A clock built from ice and dust, constructed billions of years ago in another stellar system. Set into motion by solar heating during perihelion passage, now ticking away as internal stresses find release through episodic venting events. This pulsating behavior might represent how interstellar comets evolve naturally. Perhaps all visitors from beyond undergo similar transformations when they encounter stellar heating after billions of years at interstellar temperatures. Perhaps the transition from frozen dormancy to active sublimation doesn't happen smoothly, but through stepwise releases as different compositional layers and structural regions respond sequentially to heating. 3. I-Atlas might be showing us universal processes that all interstellar comets experience. Processes we never observed before because the previous 2 confirmed visitors either showed no activity like Oumuamua or passed through too quickly for detailed monitoring like Borisov during its brightest phases. The periodic brightness pulses raise fascinating questions. How long will this pulsating behavior continue? Will it persist as the comet moves farther from our star and cools? Or will activity eventually cease as thermal energy dissipates and volatile reservoirs deplete? Each pulse potentially reveals internal structure. The timing between pulses constrains thermal conductivity and depth of volatile reservoirs. The amplitude of brightness changes indicates the amount of material released per event. The spectral signature during pulses versus between pulses shows compositional variations between different active regions or layers. This is nature providing a diagnostic tool. The comet is broadcasting information about its internal composition and structure through these periodic outbursts. If we can decode the pattern, we learn about construction from billions of years ago, preserved, unchanged, until solar heating activated this ticking mechanism. Right now, 3I Atlas faces a frustrating observational challenge: solar conjunction. The comet's position places it nearly behind our star from Earth's perspective. Solar glare creates overwhelming background that drowns any faint comet signal. Telescopes cannot point near solar position without risking instrument damage and obtaining no useful data. Nearly invisible. hidden behind the stellar brilliance that gave it temporary life through heating, but now blocks observation of the consequences of that heating. This gap in coverage is unfortunate but unavoidable. Orbital mechanics determines viewing geometry. We observe from Earth's fixed position as both our planet and the comet follow their separate paths through space. Sometimes geometry favors observation. Sometimes it creates blind spots. Currently, we're in a blind spot, but visibility will return. In coming months, the angular separation between Comet and our star will increase as both objects move along their trajectories. 3. I-Atlas will emerge from behind solar glare into observable sky regions. Ground-based facilities in Chile and Hawaii stand ready. The European Southern Observatory's Very Large Telescope, Subaru Observatory atop Mauna Kea, specialized instruments capable of detecting faint objects and obtaining high-resolution spectra. When visibility returns, these facilities will observe comprehensively. What will they find? Has the brightening continued during the observation gap? Are brightness pulses still occurring? Has the periodic pattern changed? Did perihelion heating trigger transformations that are still evolving as we wait to observe results? Space-based platforms add crucial capabilities. James Webb Space Telescope, with its extraordinary infrared sensitivity, can detect molecules and dust properties invisible to ground-based observation. Webb might characterize the unknown compounds previous spectroscopy detected but couldn't identify, determine molecular structures, reveal trace species present in tiny abundances. Europa Clipper, traveling outward toward Jupiter, might encounter residual dust and gas that 3I Atlas released months ago. Material now dispersed across millions of kilometers of space, but still detectable by sensitive instruments. If Clipper samples this debris field, it would represent humanity's first direct physical contact with interstellar material. Not remote spectroscopy, but actual particles impacting detectors. Laboratory quality measurements of compositions and isotopes, isotopic ratios, are particularly valuable. Different stellar environments produce different isotope abundances through nucleosynthesis. Carbon-13 versus carbon-12, oxygen isotopes, nitrogen isotopes. Measuring these ratios precisely constrains formation conditions, reveals information about the parent star's mass, age, and chemical evolution, places 3I Atlas in the context of galactic chemical enrichment patterns spanning billions of years. If Clipper detects unusual isotopic signatures in 3I Atlas debris, the mystery deepens further. Exotic isotope ratios would indicate formation around stars with nucleosynthesis, very different from our solar system's central star. Perhaps metal-poor ancient stars from the early galaxy, perhaps massive stars that produced unusual element distributions. The isotopes would tell us definitively. 3. I-Atlas may appear silent to casual observation, a faint, fuzzy patch visible only through telescopes, easily overlooked among countless other celestial objects. But the scientist analyzing its properties is broadcasting valuable information continuously. Every photon carries data. Every spectral line reveals chemistry. Every brightness variation indicates physical processes. The comet is sending messages, teaching lessons about environments beyond our reach, delivering samples we cannot otherwise obtain. It's showing us that our solar system isn't isolated, not a lonely island in cosmic ocean. We're part of a much larger story, a galactic ecosystem where material moves between stellar systems, where chemistry formed around one star can travel for millions of years and arrive at another star system carrying preserved records of its origin. Interstellar visitors aren't rare anomalies. Statistical models suggest dozens pass through annually. Most remain undetected. too small or too faint or arriving at inconvenient angles, but they're here constantly. A population of wanderers moving through the space between stars, carrying samples of galactic diversity. 3. IATLAS represents the purest piece of alien material accessible to current human technology. Not alien life, but alien chemistry, material formed under conditions different from our local environment, composition reflecting stellar evolution pathways we cannot study directly. Physical samples from cosmic history, preserved unchanged for billions of years. This is as close to touching another stellar system as we can get with current capabilities. We cannot send probes to other stars. Travel times are measured in thousands or millions of years, even at speeds far exceeding anything humanity can currently achieve. But the galaxy sends samples to us, free delivery of materials we could not otherwise reach, natural sample return missions that cost nothing and provide data impossible to obtain any other way. And 3i Atlas is teaching us that these visitors don't conform to local templates. Chemistry varies. Behavior differs. Properties we thought universal are actually specific to our formation environment. The galaxy creates more diversity than our limited experience suggested. Is 3i Atlas a ticking cosmic mystery? Absolutely. Brightness variations that defy thermodynamics, periodic pulses suggesting internal processes we don't fully understand, chemistry preserved from ancient galactic history, behavior that forces revising models built on studying thousands of local comets. But perhaps the deeper question is whether we're finally beginning to understand what the universe has been hiding in plain sight all along. That stellar systems aren't isolated. That material travels between stars. That chemistry from one system can deliver itself to another through natural processes operating continuously throughout galactic history. 3. IATLAS is showing us this cosmic truth through its anomalous brightening and mysterious pulses, through chemistry that reveals formation in environments unlike our own, through behavior that teaches us our frameworks are incomplete. When visibility returns in coming months, telescopes will observe what perihelion heating ultimately created. Whether brightening continues or fades, whether pulses persist or cease, whether the chemistry evolved or remained constant. Every measurement adds understanding. And when the next interstellar visitor arrives, because more will inevitably come, we'll be better prepared. Better instruments, better models, better questions informed by what 3i Atlas taught us about the diversity of materials traveling through our galaxy. The ticking cosmic mystery continues, hidden temporarily behind solar glare, but soon to emerge into view again, where waiting telescopes will decode whatever messages it continues broadcasting from the darkness between stars. Comment below, do you think 3i Atlas will fragment before it leaves our solar system? Subscribe for updates when new observations begin. When telescopes capture fresh data showing what happened during the observation gap, when spectroscopy reveals whether the chemistry transformed, when brightness measurements determine if the periodic pulses continued or evolved into new patterns. 3. IATLAS is still out there, still ticking, still releasing energy through processes we're working to understand, still carrying chemistry from another stellar system through our cosmic neighborhood. And we're watching, learning, discovering that visitors from beyond don't just pass through silently, they broadcast information, deliver samples, challenge assumptions, force growth in our understanding of how chemistry operates throughout the galaxy. The ticking continues, the mystery deepens, and the answers are coming when visibility returns and instruments can finally observe what this ancient wanderer is doing in the darkness beyond our view.